Okay, what we're going to look at in this section are different applications of using the derivative to kind of solve out some word problems. And it's actually really interesting how all this works. And the type of problems that we work are called optimization problems or modeling with optimization or max-min, something along those lines. And basically what we're trying to do is take some function that represents data or a scenario and determine what's the maximum amount of things that could happen or what's the minimum amount of space that's used or something along those lines. So a few things to keep in mind while we're working on this. Number one, when you're working these problems, trying to understand exactly what the problem is asking. Sometimes that can be really difficult, so look at the whole problem first. Read through the problem. Is it a situation you may be familiar with or have some understanding to? And then you can dive in deeper and find the more specific items to help you set your problem up. Number two, develop a mathematical model. You may need perimeter, or you may need area or volume. You could need who knows what, but probably some sort of literal equation that you've used in the past to find circumference of a circle or the volume of a cylinder or the area of a pyramid. You're probably going to need something along those lines, so you'll need a model to use. You will want to graph the model. Graphing always makes things a lot easier to deal with. It gives you a good uh, way to see exactly what's happening with your information. So a lot of times some sort of graph is really beneficial as well. You want to find critical points and endpoints. So if you're looking at, say, the area of a box, the box can only be certain dimensions, and those would be your endpoints. You want to check those guys. You also want to be able to find where your derivative is equal to 0 or does not exist. Those are critical points and can help you. And then you want to interpret what your solution is. What have you discovered? What have you found? And a lot of times we're looking for a solution that makes sense. So if I'm looking for the area of a box and I know that this box should have about 12 square inches and I get something along the lines of 6 miles, there's probably an error in there. Okay, so use your brain a little bit here. If you get some really wacky answer, that's not what you're looking for. So go through and double check your math. So let's dive in with a kind of a simple problem here. Find two numbers whose sum is 20 and whose product is as large as possible. So if we're going to find two numbers whose sum is 20 and whose product is as large as possible, it's one of those situations where we're going to say, hey, x plus y is going to be equal to 20. The problem is we can't really take a derivative of two separate things. We want one specific deal. So what I'm going to do is I'm going to say I'm going to let x be my first number choice. And remember, I can only go up to 20. So if I pick x to be my first number, then 20 minus x would be my second number. So those are the two things that I'm dealing with. Now the whole problem, find two numbers whose sum is 20 and whose product is as large as possible. Well, if I add these two guys together, I'm going to get 20. So now I just need to check out the derivative or I need to check out the product of those. So I want f prime of x to be as large as, or f of x to be as large as possible, and I'm working with x times 20 minus x. So, uh, it's going to be easier on this guy to refer to him as 20x minus x squared. Go ahead and find derivative. And set it equal to 0. Okay? And when you do this, you can divide a 2 out of everything, and that gives us, let's see, I'm running out of space here. That gives us 10 minus x equals 0. So x equals 10. That's one of my critical points. In fact, that's the only critical point that I'm going to get. Let me just check real quick. I'm pretty sure 10's my only critical point from all of this. Yep. So what does that mean? That means that if I take this number x equals 10 and I check it with my other number 20 minus x, that would be 20 minus 10. If I multiply these two guys together, I get 100. If I add them up, I get 20. And when I multiply them together, that is the largest possible product. Okay, I've got other numbers that add up to 20, but when I multiply them together, they aren't 100. Like, for example, 18 plus 2. 18 plus 2 is 20, but 18 times 2 is 36. Or 16 plus 4. 16 plus 4 is 20, but 16 times 4 is 64. 11 plus 9 is 20, but 11 times 9 is 99. So I've got all these different things to check. How do I know which one is largest? Well, set up a mathematical model, take a derivative and find critical points, and then solve it. And that's how it works. So this is a simpler problem right here. We'll check out some other ones on the following slides that are a little bit more exciting. All right, here we've got a rectangle that's going to be inscribed under the one arch of the sine curve. What is the largest area the rectangle can have, and what are the dimensions? So let's just talk about this for 1 second. I'm going to take and create inside one arch of the sine curve a rectangle, and I want this rectangle to have a max area, so I need to find the area of this rectangle, which means area of a rectangle is going to be x times y. So we'll call, for now, we may change this, we'll call this x. Let me do that in different colors. We'll call this guy right here x, and I just drew this at random. We're going to totally nail it down and make it perfect. We'll call this y. So here's x and y. So we want the largest area the rectangle can have. What would the dimensions be? So we've got to figure this out. We want the largest rectangle. So I somehow have to get into terms this x and y deal so that they're related. Well, here's the thing. If I look at this first x right here, if I look at this x right here, this value of x, this legit value of x, I'll call him x1. Let me just make him a totally different color so that way we're not confusing ourselves. I'm going to look at this distance right here, this value of x from the origin. Okay, I'll call him x1, he's red x. This point right here would be f of x1, and that would be my height. Okay, so the height at this point would be x1 sine of x1. Okay, now why do I say that? I say that because we've got to figure out how to identify this rectangle and get a max rectangle under this arch of a sine curve. All right, and so when I do that, notice that whatever value this is right here, I'm going to match it on this end as well. It's going to be the exact same because I'm going to move in the same number of units from both sides of the end of my sine curve to create my rectangle. So my rectangle is going to be centered inside that arch, under that arch. So this distance right here is going to be the same distance no matter what. All right? And so when I do that, that's got to be part of my reasoning and part of the things that I got to think of when I do this. So let's just think about this now. If my whole arch of my sine curve starts at 0 and goes over here to pi, and I use up this much space right here and this much space right here, and again, we don't know where x stops. How much space am I doing? How long is my rectangle? And the answer is the length of my rectangle is going to be pi minus 2x. Okay, 2x. Why? Because I've got x number of units here that I'm going to take away and come in to start creating my rectangle, and I've got that same number right over here on this side. Okay, so whatever I move in from the 0 to get into my rectangle is going to be the same distance I move in from my pi to start my rectangle, and if I move that same distance twice, that's 2x. Okay, that's my length. So my height then, which we talked about just a second ago, my height is going to be whatever value that the sine is of x1 at that particular point. That's going to be the height of my rectangle, okay? So now I've got a rectangle. Look, x and y right here, my x and y. So this x right here in pink now, come back to pink, this length from here to here is going to be pi minus 2x1. And my height, we just discussed, is going to be f of x1. Okay, so what can I do? I've got now a way to relate these with a mathematical model. I've got an area equal to length pi minus 2x. I'm going to just work with 2x. It'll be a little easier, but it's at x1 distance times the sine of x. So one of the things that we had to do was find our critical point. Well, how do we find our critical point? Find a derivative, set the derivative equal to 0. And in this case, there's a couple different things that we can do. I think it's going to be a little easier to just use the product rule here. But if you want to go ahead and multiply and distribute through the sign, you could do the same thing. The product rule, though, is not hard. It's simply the first term times the derivative of the second term plus the derivative of the first term. Well, the derivative of that, and here's our terms. I'll just show you real quick. Here's one, here's the other. The derivative of my pi minus 2x is just negative 2 times the second term. So my equation then looks like this. Pi minus 2x cosine x minus 2 sine x. Okay, so there's that guy right there. And what we need to do is we need to figure out where the derivative is equal to 0. So how are we going to do this? This looks really tricky. Well, we've got to see if there's a way that we can factor this guy out a little bit. What I'm going to do is I may have to actually use a graphing calculator. Let me just double check here. It looks like I'm going to have to use some sort of graphing calculator to find this. I don't know that we can get an answer that's going to work, since it's a trig function, with a radian measure that we would know. But I would have pi cosine x minus 2x cosine x minus 2 sine x equals 0. And there is nothing in all three of those that I can factor out. So what we're going to do is we're going to graph this, and we're going to find all the places that this guy equals 0, and we're going to limit our search between 0 and pi. Okay? The reason that we're going to do that is because we can't have a rectangle that starts over here somewhere in the negative numbers, and we can't have a rectangle that starts over here larger than pi. So get your calculators out, pause the video real quick, and see if you can determine those values where you get your graphed across the x-axis on your calculator. All right, did you use your calculator? What'd you get? If you graph this line right here, you should get that x equals, what I got was 0.710, and we can write a 4 here if we want, or a 5, but what I would encourage you to do is truncate at 3 decimal places. So 0.710 is my value of x, which occurs between 0 and pi, and it does, that allows me to have the largest area rectangle. Okay, so what does that mean? That means that my length then is going to be pi minus 2 times 0.710. That's the length, okay, times, I shouldn't use an x there, should I? That's terrible. Times the sine of 0.710. And when you punch all that in together, that's going to give us the area of the rectangle right here in blue that fits under one arch of the sine curve. So let's write it down here so a little bit bigger we can see it. We're going to have pi minus 2 times 0.710 times the sine of 0.710. So punch that into your calculators real quick and see what you get. Alright, so when you punch this into your calculator, you should get 1.12 units squared. So I think this is a really fascinating problem, and it shows us all the different tools that we have to do. And does 1.12 units make sense? Just think about it for a minute. That's small enough. That sounds like something that could work. You know, if we got 27, I don't know. That's a little bit much, I think. But 1.12 units, that sounds like something that could work. So there you go. There's an optimization model for finding a rectangular shape under a sine curve. Alright, on this problem we've got an open top box that we're going to make by cutting congruent squares of length x from corners of a 20 by 25 inch sheet of cardboard and bending the sides up. How large should the squares be to make the box hold as much as possible, and what are those dimensions? So let's go ahead and give ourselves a box that we're going to work with here, and it's supposed to be 20 by 25. That doesn't look too bad actually, okay? And what we're going to do is we're going to say that this is 25 right here and this is 20 right here. Now, here's what we're going to do. We're going to take x units that we're going to cut out of each corner of the box. And when we cut those corners out, that's going to give us the edge of the box. So try this at home even. And take a flat sheet of paper, cut out squares in each corner, and when you fold what's left straight up, you're going to create a box. And we want to create a box with maximum volume. And volume is equal to length times width times height. Well, on this particular problem, one thing that we're going to learn, one thing that we have learned that we will use, is that these x's, that's our height. So x is equal to height. Length, I don't like the way I wrote that. Let me write it the other way around. Height is equal to x. Length we need to find, and width we need to find. So if I take x units from here and x units from here, then this length is no longer 20. It stops short by 2 x's. So this length would be 20 minus 2x. The other one, if you look at this guy, we're taking x units off from both sides here. That gives us a 25 minus 2x length. Alright? And so what's the volume of my box going to be when I fold the sides up? The volume is going to be x times 20 minus 2x times 25 minus 2x. So what we need to do is find the derivative of that, and I think it'll be easiest if we FOIL this thing out first and put all the like terms together and then come back through and take a derivative. So I'm going to distribute my x real quick, and that's going to be 20x minus 2x squared times 25 minus 2x, and then just multiply this part out. So 20x times 25, that's 500x, and then 20x times the negative 2 is minus 40x squared, and then negative 2x squared times 5, that's 50x squared, and then negative 2x squared times negative 2x plus 4x cubed. So here's my volume, and when I clean this up a little bit more, I end up with 500x minus 10x squared plus 4x cubed. All right. All right, I caught a mistake here. I should have this guy right here should be a minus negative 2x squared times positive 25, which makes this a negative 90. There we go. There's my volume. And in order to find the max volume of this thing, I need to now find the derivative. So 500 then minus 180x plus 12x squared. So what I would recommend on this, it doesn't look like it's going to be anything that would factor. When I set this thing equal to 0, is 500, I don't know if any of these numbers are divided by 12. Let's see. 180 divided by 12 is 15. 500 divided by 12 doesn't work. What about 500 divided by 6? I don't think that's going to work. So I can divide a 2 out of everything. That gives me 250 minus 90x plus 6x squared. But I'm pretty sure that doesn't factor either. So you've got two options then. One is to use quadratic formula, and the other one is to graph it and find where it crosses the x-axis. Now, because we need to know exactly the exact value of x, like how much to cut, I would prefer a decimal answer here. Sometimes you can get away with using the square root, but if you were to give me an answer of x of the square root of 23, that doesn't help me out very much. That's between 4 and 5, closer to 5, not so much 4. But if you told me I needed to cut 4.87 inches in, that gives me a lot more to work with just for my own personal taste. So what I would recommend right now is that you go ahead and graph 6x squared, 250 minus 90x plus 6x squared. Graph that, find where it crosses the x-axis. Now, let's talk about values of x that we can use. Think about this real quick. When I cut these x values out of my rectangle, I can, in theory, cut all the way to the center of a side, okay, in theory. But I can only cut to the center of the shortest side, and then I run out of room. So what I'm going to do is I'm going to say that I can only cut in 10 inches. So when I am looking for values of x, I'm going to put a restriction that that value of x has to be larger than 0 and less than, I don't know why I wrote equal to, it needs to be larger than 0 and less than 10. So that's the restriction that we're going to look at. So when you graph this guy and you look for the zeros here, you have to pick then the zeros that are between 0 and 10, and there may be 1 or 2, but those are the only ones you can use. If you get one that's a negative value, you can't use it. We're going to make positive cuts. If you get one that's like, if you get an x value of say 11.7, you can't use that. That's too much. Okay? So when you punch this into your calculator, you're going to get two things. You're going to get x equals 3.68. and you're going to get x equals 11.32. So when you graph it and find those zeros, these are the two zeros you get. This guy we're not going to use. Why? Because he's outside of the range of values that are possible for this particular problem. So the answer then for us is going to be this x equals 3.68. Okay? What does that mean? That means that if I cut in wow, that's really ugly. If I cut in 3.68 units from each corner on each side, that'll give me the height of my box. And so when I plug 3.68 in for my length and 3.68 in for my width, this will give me the dimensions of my box. So when I punch those in, 20 minus, let's see here, I'll just punch it in for 20 minus 2 times 3.68 is 12.64. And 25 minus 2 times 3.68 is 17.64. So these are my dimensions, 3.68 by 12.64 by 17.64. Those are my dimensions. My volume for that particular guy, then you just multiply all those dudes out. And you should get, I think, 820.53. Let me just double check. 3.68 times 12.64 times 17.64. I get 820.53 units cubed, and that would be the volume of this box for this problem. All right, this is a toughie. There's a lot going on here. You may need to watch this part of the lesson a couple times, or at least maybe tweet a question or ask. But we want to design a can shaped like a right cylinder that holds 1 liter of liquid. What dimensions use the least materials to make that can? Now, we're not going to get into super detailed discussions about the thickness of the material or things like that. We're just going to pretty much talk about surface area only. For simplicity's sake at this juncture. We may talk about thickness of material later, but we want to make this can right here. We want to make this can, and we want it to hold 1 liter of liquid. Now, 1 liter of liquid, I've got it on good authority, is equal to 1,000 centimeters cubed. Okay, 1,000 centimeters cubed. So if we're going to hold that, that's a volume. That's a volume. Well, if that's what my volume is, then I need pi r squared h. That's going to tell me the volume of my cylinder. And in this case, we know that that needs to equal 1,000 centimeters cubed. Okay? Now, the other thing that's going on here is we need surface area. We need surface area of my cylinder because that's the actual stuff that wraps around the cylinder and gives it its shape. That's what we're wanting to minimize those dimensions. Okay, so we're going to minimize, which I smell a derivative coming. But for surface area, then, we're going to use this guy right here. We're going to use 2 pi r squared plus 2 pi r h. All right, so this is my surface area one, and this is the one that we want to minimize, okay? We want to minimize this guy right here, but there's 2 different variables running through this problem. I've got an r and an h. Now, the cool thing is I've got an r and an h over here, so maybe if I were able to rewrite this relationship right here and have it say h equals, I could replace this h with that thing, and then I would only have the 2 variables. Okay, so let's look at this real quick. Let's go ahead and solve this guy out. I've got, I can divide both sides by pi r squared. And this would give me my new h right here. This is my new h. All right, h equals 1,000 divided by pi r squared. I can put that in for this h right here because they're related. Why? The can is the same height in both pieces. It's the same height for the volume as it is for the surface area. That doesn't change. So my new equation for my surface area becomes 2 pi r squared plus 2 pi r h. 1,000 over pi r squared. Okay. What do you think about that? That doesn't look too bad, right? So we can simplify this by one more step here. The front part doesn't change much, but notice back here the pi's can cancel. I've got to remember this is all over 1. This is all over 1. So this pi and this pi cancel. This r and one of those r's cancel, and 2 times 1,000 is 2,000. So what I end up with is 2,000 over r. Now, that doesn't seem too bad. That doesn't seem too bad at all. So what can we do here? I'm going to rewrite this equation that we're working with over here. This is my surface area equation. 2 pi r squared plus 2,000 over r. Or it might be easier on this problem to think of it this way. 2 pi r squared plus 2,000 times r to the -1. Because, why? We're going to have to take a derivative. Why? Because we want to minimize the amount of material used on our surface area. Okay? And so what I'm going to do is I'm going to go ahead and take derivative of this guy. Remember that pi is constant. He doesn't change. 3.14, he never changes, never has, never will, he's not going to. So the derivative becomes 4 pi r plus, and then actually minus 2,000 r to the -2, or 4 pi r minus 2,000 over r squared. Okay, both of those equations are going to be the same. And what we're going to do is we're just going to set this guy equal to 0 and solve him out. Set it equal to 0, solve him out. So I'm going to end up with -2,000 over r squared equals -4 pi r. I just moved one guy over. I'm going to multiply both sides by r squared. So -2,000 equals -4 pi r cubed, and then I have to get the r all by himself, so I'm going to divide both sides by that 4 pi. And it looks like I'm headed for another calculator issue here. So I've got r cubed equals, what is that? 1,000 over 2, 500 over pi. 500 over pi. That's not a number I carry around in my back pocket with me, to be sure, but what I need to do now is get the r all by itself, and the best way to do that is to take the cube root of everything, or just raise everything to the 1/3 power. And when I do that, I will get a value of r that will be my max value, and it'll be my min value for the radius, to help me find the least amount of material that's going to be used. So when I punch this into my calculator, what I'm going to end up with is 5.42. All right, so we found part of the problem here. We found the radius of the right cylinder. So remember on this, we had two variables here. We had a radius and a height. So the radius of my right cylinder can is 5.42. Now, I need to know what the height is. Good thing we have an equation for that right here. Looky, right here. See it? See that equation right there? See it? Right there? What we're going to do now is we're just going to plug in our value of r into that and punch it into your calculator and see what you get. And so when I punch mine in there, I hope I get 10.84, because that's what it should be. 10.84, man, what a relief. Now, what dimensions are we talking about here? That's the next crucial question. Well, remember at one point in time we had converted everything around into centimeters way back here at the beginning when we were talking about liters. So we're going to call this centimeters here. We're going to call this centimeters here. And this then is the dimensions of our right circular cylinder that uses the least amount of material for the surface area. All right, our company, Bulldog Manufacturing Inc., has revenue that matches this equation right here, not R of x equals 9x, and it has cost that match this equation right here, where C of x is equal to x cubed minus 6x squared plus 15x, where x is in thousands of units. I'm thinking twinkling Christmas festive holiday lights, okay? What production level will maximize our profits? Well, one of the cool things about this that our book talks about is that you get maximum profit where marginal revenue equals marginal cost. Well, what was that? Marginal revenue is the same thing as R prime. Marginal cost is the same thing as C prime. So all we have to do is find the derivative of these two functions and set them equal. That's going to be our model. Then we find our critical points from that, and we're off and running. So if I have R of x equals 9x, so R prime is 9, C of x is equal to x cubed minus 6x squared plus 15x. So C prime is equal to 3x squared minus 12x plus 15. And all we have to do is set these guys equal to each other and solve it out. Okay, set it equal and solve it out. So 9 equals 3x squared minus 12x plus 15. And we're going to subtract 9 from both sides and make a 0, because that's how you solve a quadratic. And not an equal sign there. 15 minus 9 is 6, last I checked. I don't know. I'm divide out by 3, because I've got a 3 in each term. So x squared minus 4x plus 2 does not factor. So into quadratic equation, or you could graph this and see where the graph crosses the x-axis. Now keep in mind, we want to have a positive number of things that we're creating. So if we get a 0 that tells us that we have to create negative 27 units, we can't use that because we're going to create units. So go ahead and punch this into your calculator real quick, or use quadratic formula, or graph it and see where you end up. Pause the video if you need to, and come back to me when you think you've got an answer. So when I punched it in, I get two things. I get 0.586, and I get 3.414. And these are in thousands of units. Okay, these are in thousands. And this is how many units I would need to create in order to maximize my profit. So that's really a really interesting way to look at maximizing profits for your company. If you have a revenue equation, you've got a cost equation, you can take the derivative of both of those things and set them equal to each other. And wherever your zeros are, that's where your max profit occurs. Pretty cool.